So here's a simple thing. What is the sum of the degrees of all the vertices in this graph? If you do this, so the thing is you will construct a degree sequence. So this is 2, this is 2, this is 2, this is 1, 2, 3, 4, and this is 4 as well. Okay, and if you sum them, so you get 14. Okay, 8 plus 6 is 14. Yeah. Okay, but the plan okay, so this number is called the total degree of the graph. Okay, it's not a very sort of standard term, but it's used in probably in your book. Total degree of a graph is just the sum of the degrees in your graph. And here's a fact which says that the total degree is 2 times the size, 2 times the size of the asset. और ये हमने last time prove भी किया था. Okay, we proved it last time. Here is a question which I'm going to ask you. Look here, okay? I want you to construct a 3 regular graph with 5 vertices. Okay, so this graph should have 5 vertices. Let's call them V1, V2, V3, V4, and V5. Okay, and this must be 3 regular. What does this mean? Does anyone remember? Yeah.
Every vertex got 3 neighbors.
Yeah. Every vertex has 3 neighbors. So how do I do this? How do I construct a graph where every guy has a 3 neighbor and there are 5 vertices? Can anyone think of a way to do this? So these are my vertices.
पेंटागन में बनाएंगे.
Okay, so if I make this pentagon thing, which I was saying, so everyone would have a degree 2. Okay, I still need to
make a star.
Yeah.
Make a star in it.
Make a star in it.
Diagonals बन जाएंगे ना.
You can make a star inside the pentagon and then join each edge of the star.
So the thing is, if I add a star inside this thing, I will have added 2 neighbors to each node. Okay, and I need to add 1 neighbor because I have already added 2 neighbors to every vertex.
There's another way. If you connect, if you make 2 diamond kind of shapes like kite shapes and then connect the inner vertices together.
So if we place 4 vertices and the 5th vertex inside the 4 vertices and connect them.
Okay, so here's the thing. I'm thrilled to see the interest in solving this problem. But the thing is, it's not possible to construct such a graph. And can you guys see why?
Fact जो ऊपर लिखा हुआ है.
Every time we draw, will add 2 paths.
So the thing is, this is a 3 regular graph, which means the degree of each guy is 3, and there are 5 vertices. So the sum of degrees in the total degree would be 15, right? And this is supposed to be 2 times the number of edges. Okay, but 2 times the number of edges should be an even number, right? It should not be an odd number. Okay, so you can't construct this graph because the sum of the degrees in the graph should be an even number. It's not possible to construct a graph in which the sum of the degrees is an odd number. Okay, this is this fact tells you that it's not possible to construct this graph. All right, does it make sense to everyone?
Yes, sir.
Yes, sir.
Awesome. Okay. So here's a little fact. So the number of edges in a graph is the mean degree times n over 2. मैं थोड़ा सा इसको ऐसे करता हूँ कि यहाँ से 2 हटा देता हूँ, यहाँ से भी 2 हटा देता हूँ और यहाँ पे 2 लिख देता हूँ. Okay, so 2 times the number of edges, which we know is the sum of the degrees, is more than n times the minimum degree and is definitely less than n times the maximum degree. Okay, so हम minimum degree को this small delta से denote करते हैं और maximum degree is this large delta. Okay, so since this is the sum of the degrees, if I replace every degree with the smallest degree, I would get a number which would be smaller than this, or at most this. Okay, if I replace each number with the largest of those numbers, I would get something which is at least this much. Okay, so the sum of degrees, or 2 times m, is n times small delta, and it's less than n times the large delta. Okay, so in here, for example, minimum degree is 2, and the maximum degree is 4, right? 1, 2, 3, 4. This is wrong. So maximum degree is 4. So the number of edges in here should be greater than and how much is n? 5? 5
It's
times
principal.
2 over 2, and it should be 5 times 4 over 2. Okay, so that's sort of a result that you should keep in mind, that you have this relation of the number of edges with the minimum degree and the maximum degree. Okay, if I tell you something about a graph, I don't give you the whole graph, I just tell you the minimum degree or in the maximum degree, you can still say something about the number of edges in that graph. Okay, let's say if there is a graph and I hide the graph, I don't tell you the graph, I just tell you how many vertices are there and what's the minimum degree and what's the maximum degree. You can still deduce something about the number of edges in this graph. Are we good?
Yes, sir.
Okay. All right. So there are these 2 terms used for graphs: a labeled graphs and an unlabeled graph. A labeled graph is a graph in which you give names to the vertices. अभी तक हमने जितने ग्राफ देखे हैं, they are all labeled graphs. Okay, हमने उन सबको label दिए हुए थे. We call the vertices, हमने नाम रखे हुए हैं. But if someone gives you a graph and they say that it's an unlabeled graph, what it means is that उसके जो नाम हैं वो अगर आपको दिए भी गए हैं ना, तो वो arbitrary हैं. Okay, so for example, I give them name 1, 2, 3, 4, 5. Okay, if this is an unlabeled graph and someone, instead of calling these vertices by these names, if he calls them 1, 2, 3, 5, and 4, even then they are talking about the same graph. Okay, anything that they say about this pink labeling of the vertices should be true about the black labeling as well, if this is an unlabeled graph. Okay, नॉर्मली जब भी आपको अनलेबल्ड ग्राफ गिवन होता है, उसमें आपको वो वर्टिसेस के नाम नहीं बताते, दे जस्ट गिव यू अ लिस्ट ऑफ एजेस. ओके, और एजेस के अंदर जो लेबल्स होते हैं वर्टिसेस के, वो आर्बिट्रेरी होते हैं. ओके, इट डज नॉट नेसेसरीली मीन कि वो जो नाम रखे हुए हैं दे आर फिक्स्ड. ओके, जैसे फॉर एग्जांपल यहाँ पे ये ब्लैक लेबलिंग है, इट्स नॉट अ फिक्स्ड नेमिंग ऑफ द वर्टिसेस ऑफ द ग्राफ. Is the concept of an unlabeled graph clear to everyone? Shaviz?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay. Cool. So here is the problem. It's a very famous problem. It's called graph isomorphism problem. How many people have heard of this problem before? All right, then it's gonna be interesting. So the thing is, this problem you are given to unlabeled graphs, and the question that you need to answer is whether they are actually 2 copies of the same graph or not. Okay, is there a labeling of the vertices of these 2 graphs in which you can actually show that they actually correspond to the same single graph.
No, sir.
No, sir.
So the question is, are these two graphs same or not?
We will count vertices. We will check degrees.
Same है sir.
So the thing is, जैसे मैं ख्याल में अनस कह रहा था, you can look at the number of vertices, okay, which is you can also look at the number of edges. You can also
And
look
the
at the
degree.
Yes,
yeah.
sir.
You can also look at the degree sequence. What else can you do?
Number of bijections.
Yeah, yeah. That's the sort of. So the thing is, what you could do is you can find a bijection from. So if all of these things are true, okay, if the number of vertices in here, the size of V1 is actually equal to the size of V2, then there exists a bijection, okay? There should be a bijection from the vertices in this graph to the vertices in this graph, okay? So what you could do is you can enumerate all bijections. And then for each bijection, you can check whether you end up with the same set of edges or not. Okay. So for example, if I say that, so this is sort of थोड़ा सा मुश्किल ग्राफ है. मैं आपको एक आसान ग्राफ को बताता हूँ जिसके अंदर हम ये काम बहुत आसानी से कर सकते हैं. So for example, I'm looking at K4. Okay. There are these two copies of K4, which look, let's say, different to me. Okay. These are, let's say, labeled 1, 2, 3, 4, and these are labeled A, B, C, and D. Okay. So a bijection is 1 to, let's say, B, 2 to D, 3 to C, and 4 to A. Okay, that's a bijection. And what I can do is, after I have this bijection, what I can do is I can look at this graph and I can see that 1 is connected to 2, 3, and 4. So D in here must be connected to the corresponding node of 2, which is D, corresponding node of 3, which is C, and corresponding node of 4, which is A. Okay, so I go and look at B and see what are the neighbors of B in this graph. Okay, if they are exactly the same corresponding neighbors as they were in the original graph, तो फिर I go on and check it for the next guy. I go and check it for 2, then I go and check for 3, and go and check for 4. Okay, and that's it. And that's the way to actually solve this problem. That you enumerate all bijections, and for each bijection, you check whether they correspond to the same graph or not. Okay, but as you can see, that this is a very laborious task. How many bijections are there for an n vertices graph?
10.
So there are, how many bijections are there?
10.
Whoa. Hold on a second. Boy, we are in a discrete class. How many bijections are for this graph? 1, 2, 3, 4 to A, B, C, D?
4.
No. Boy, no.
6.
No. How many bijections are there? How many bijections are possible? ये तो एक bijection है ना? This is an arbitrary bijection जो मैंने अभी create किया. Okay. अब इसी तरह you can create another one in which you place, you say कि 1 goes to D, 2 goes to C, 4 goes to, let's say,
क्या combinations होंगे?
A, and 3 goes to, I don't know. How many bijections are there?
N by 2 if n is even, and n by 2 plus 1 if n is odd.
No, there are a lot more bijections.
And
And you
factorial.
should,
4 factorial. 4 factorial.
4 factorial.
yeah. So the thing is, again, you are looking for a bijective function from a set of n nodes to a set of n nodes. Okay, so for the first guy, you have n options. And once you have picked an option, for the next guy there are n minus 1 options. Okay, so 1 के लिए मैंने d pick कर लिया. अब 2 के लिए there are 3 options. Okay, 4 के लिए there are 2 options. 3 के लिए there is only 1 option. So there are 4 factorial bijections for this guy, and there are n factorial bijection for n vertices graph. This was an easy question. N. So there are n factorial possible bijections, which means it's a huge number, right? For slightly large graphs, for example, अगर आपके पास 100 nodes का graph है, this it becomes really almost impossible to actually enumerate all bijections and check their graphs same. ये वाला जो checking वाला काम है, that's not actually that tough. It's easy. For each node, you just need to go and check the vertices. Okay, that's not going to take a lot of time. But enumerating the bijections is going to take a lot of time. Okay. All right. So how about these examples? Are they the same graph or not?
They are.
Yes, they are.
They are.
Because every
Yes, sir.
vertex has degree 3.
That's not enough. So मैंने आपको जैसे कहा, it's possible that there are two graphs with the same set of vertices, with the same number of edges, with the same degree sequence, and it's still possible that they are not isomorphic. Okay, so that's not enough information to say that their degree is the same. Okay. So you will have to check all possible bijections. This case, these two graphs are actually, I think, bijective. Okay, let me just make sure that they are.
सही, ये तो बहुत लंबा नहीं हो जाएगा लेकिन.
Of course, it will be. It's a really hard problem. इसीलिए तो this is sort of an open problem जो अभी तक solve नहीं हुई. Graph isomorphism के it's one of the hardest problems in computer science. So there are two sort of sets of complexity classes जो हम computer science में use करते हैं. Things that can be solved in polynomial time and things that are known to be not solvable in polynomial time. Graph isomorphism is sort of one of those unique problems जिसके बारे में हमें अभी नहीं पता कि we can solve it in polynomial time or not. Okay, मैं अभी आपको कुछ और problems बताऊंगा which are hard but we know about them कि we can solve them in polynomial time. But for graph isomorphism we actually don't know. There is evidence that we might be able to solve it, but there is no known algorithm to solve it in polynomial time. All right. I'm just give me a second. If I pick one, two. If I here. No. That position will not work. So I think this might be a good bijection. Okay, so if let me label them. Okay, 1, 2, 3, 4, and 5. Okay, once I label these 5, I think बाकी जो 5 हैं वो sort of clear हो जाएंगे. Okay, so let me call this guy 1, this guy 2, this guy 3, this guy 4, and yeah, I think this guy is 5. Okay, इसको वैसे ड्रा करेंगे तो you'll see that this is actually the same graph. All right.